Ladies and gentlemen, before or as I introduce the second Hitchcock lecture to you, Professor and the lecturer, Professor Sir Edward Bullard, I'd like, just as a way of introduction, to give you a little of my prejudices of how geology started. Now, some of you here, I think, are geology students or geophysics students, but some of you may not be quite so deeply immersed in the subject. And geology started in a rather curious way, at least what we understand it to be today. In the Industrial Revolution in England, people dug canals. And when they were digging canals, they noticed one strata on top of another strata. And this fundamentally led to the law which said that the top strata was probably younger than the bottom strata. And so geology as a subject started in England in this way. And geologists practicing in geology departments by tradition became very concerned with what they saw in the field, namely canals and the trenches which gave rise to canals. And they made maps of these and they examined the specimens which they brought back with a hand lens. Well, geologists, being a young subject in those days, they became very protective of the depredations of the other sciences, and they were pleased to call what they studied a science. And the other sciences to them were physics and chemistry and mathematics. And so to this day in England, we find geology departments, but we don't have any geophysics students, we don't have any geophysics professors, and seldom do we find geochemistry professors or geochemistry students. Geology in England is still largely immersed in the tradition which it was started when they were building canals. That's a nice prejudiced statement coming from someone who was educated there. But in America, life was rather different. In America, the geologists, possibly more hard up than they were in Britain for their one reason or another, they invited physicists and chemists to come and help them. And physicists and chemists came into the departments, and in America we have departments of geology and geophysics, whereas in England and Australia and New Zealand, the geophysicists have become a sub-department of physics, or the geochemists a sub-department of geochemistry. So in America, we are lucky to have incorporated, be overwhelmed by, included with the geophysicists and the geochemists. And as a geologist, I like to say how much I've appreciated their advice and help in the past. And of their number, Sir Edward Bullard is one of the most distinguished and the most productive and the most lively and the most entertaining. And I introduce to you tonight Professor Sir Edward Bullard for the second Hitchcock Professorship lecture.
I was told as I came in that a lot of the audience believed this to be a performance of Swan Lake. And I thought I'd perhaps better announce that I am not, in fact, going to dance Swan Lake. That is next Monday. And again, I shall not be dancing. Well, last time I talked in a fairly simple-minded way about what the bottom of the oceans is like, or are like. Bottom of the oceans is like. And the main features which I talked about were two things. First of all, the great mountain range that runs along the middle of the oceans. Slide, please. The first slide here is one that I showed last time, and the black line. No, I wanted the first slide, please. That was quite all right before. That's fine, fine. The black line represents the axis of this great mountain range running all around the world, down the Atlantic, across the Indian Ocean, across the Pacific. And I gave evidence that this mountain range was cracked in the middle and was in fact cracking open all the time. There's a row of earthquakes along it, and it's continually cracking open, and the crack is filled by lava. Well, this and other things show how extraordinarily different the oceans are from the continents. As I said last time, the oceans are a new world to the geologist, and there's no good believing that anything you've been told or seen on the continents you will find in the sea. It's quite a different place. The second great fact about the oceans that's been discovered in relatively recent times, since the last war, is that the oceans are quite young. The whole of the floor of the oceans is less than 200 million years old, less than 150 million years old, really, whereas the continents are all ages up to 4,000 million years. And it's an extremely striking thing that the oceans are young and the continents are old, and the ocean floor appears to be forming itself before our eyes. Well, these facts are surprising and were utterly unexpected. I mean, nothing is so surprising, I think, as the discovery of the youth of the oceans. It was quite unexpected, and I think one would have some reservations on the evidence I gave last time. I talked about it plausibly, because that's my business as Hitchcock professor, to talk plausibly. But I'm not sure that I would have believed it if that was all there was to it. And I want to start this time by talking about a really most remarkable piece of evidence which has come, again, quite recently, and has confirmed what I said last time, the splitting open and the formation of new ocean floor along the axis of this mountain range, and has shown, I think beyond doubt, that it really is happening. When one says beyond doubt, one always thinks of old Professor somebody or other who says he doesn't believe it, but I think there are extremely few people who don't believe it. I can think of two. No, I can think of three. There's a Russian. Well, let's have the next slide, please. It has been known for some time, since the beginning of the century, that some rocks are magnetized in the opposite direction from what you would expect. If a lava comes out of a volcano, it's all hot and glowing and liquid and runs down the side of the volcano, and then it solidifies and cools down, and as it cools down, it gets magnetized. So the bits of lava, if you knock off a bit of lava with a hammer, it's a weak magnet. And it magnetizes itself in the direction of the Earth's magnetic field. So that you've got, in a volcano, a lot of fossil compasses which show the direction of the field at the time that the lava came out. And now, of course, the compass points to the north, and indeed the rocks around Vesuvius, for example, are magnetized in a northerly direction, and also in a direction, the Earth's field in the northern hemisphere runs north and down, so that they're magnetized to the north and downwards. But, as I say, it was found 70 years ago that there are a lot of rocks that are magnetized backwards. And this very remarkable fact was discovered at the beginning of the century by some Frenchmen. And extraordinary to relate, no one ever paid the slightest attention, except a few other Frenchmen. I suppose it was that they published it in French, and they didn't go to conferences enough, and they didn't know the right people. But anyway, they were, as far as I can discover, completely ignored. I first heard about it in about 1939, and I spent some time, I was in South Africa at the time, I spent some time trying to explain it away, not very successfully, and then the war came and I had other things to think about. But after the war, the thing was taken up again, to some extent in this country, and in quite a big way in England. And gradually it became apparent that there was here a most interesting phenomenon. And finally, Cox and his friends at Stanford and at the US Geological Survey at Menlo Park showed beyond doubt that what had been happening was, in the past, the Earth's magnetic field had been reversing, and by measuring the ages of the rocks and the direction of magnetization, mostly with lavas from California, they got a timetable like this for the last 3 million years. 700,000 years ago, the field reversed. It changed from being the opposite direction to now to the present direction. Same thing happened 2.4 million years ago, the other way around. It changed from what we're pleased to call the normal direction to the reverse direction, and again at 3.3 million years. There are also some short ones, which are those dotted lines, which didn't last very long. So you've got a rather complicated and certainly very interesting and obscure phenomenon that the Earth's magnetic field had turned itself round. And the thing that really clinched it was that this same pattern was found all over the world. Well, now, what does this mean for the oceans? Next slide, please. Here is a ridge splitting open. Here's the axis of the ridge. We'll take this one. There's the axis of the ridge there. It's splitting open. The material this way is moving that way. This way is moving that. And lava is coming up here and pouring out of the bottom of the sea into the cold water, cooling down and solidifying and becoming magnetized. And it will become magnetized in the direction of the present field. And this will go on, and you'll get a whole stripe of rocks that are magnetized in the direction of the present field. Then one day, for reasons best known to itself, the Earth's field turns around and reverses, and the next bit of lava that comes up is magnetized the other way, so that you then get a stripe of backward magnetized rock. And as time goes on and the material moves away on the two sides, you'll get more and more stripes like this, spread out on the two sides of the ridge. Well, this is a rather splendid thing, because if you can identify these things and find them, you've got some idea. If you know the dates of the reversals, you'll have some idea when this bit of seafloor was on the ridge and was formed, so that you look around for magnetic stripes on the bottom of the ocean. And you can, in fact, next slide, please. You can, in fact, find these things. Here's a man called John Cleverley, who used to work with us in Cambridge. He's now gone on to greater things and is some kind of big administrator of government with the geophysics in the government. Anyway, here is the young man carrying a magnetometer. The thing that measures the Earth's magnetic field lives up here, and there's various electronics and things are put down here, somewhere away, so as to stop it disturbing it. And you throw this thing into the sea over the back of the ship, and having first attached it to a wire so you can get it back again, and a signal comes up the wire and tells you how strong the magnetic field is. You put it behind the ship, about a couple of ships' lengths behind, 500 feet behind, say, so as to get away from the magnetization of the ship. So that you can go along with this thing behind you, and a recorder going clonkety-clonk in the chart room of the ship, recording the strength of the Earth's magnetic field. And as you go over these magnetic stripes, the record goes up and down, and you get a pattern which is similar to the pattern found by Cox from examining rocks on land. You have the whole thing laid out horizontally for you on the bottom of the sea, the same story told over again. In fact, you can get the same story a third time if you like, because the sediments at the bottom of the ocean are very slightly magnetized, and if you stick a tube into them and examine very carefully down the column of sediment that you get out, you find that is also slightly magnetized as it is formed. So that you get the story 3 times over, but the one that's important to us is the one you get with this machine, because you find these stripes on the bottom of the sea, which are the relics of the magnetization of the lavas at the time they were formed. Slide, please. Oh, I've got a thing I can manipulate the slides with. How nice. Well, this is some of these stripes. This is Iceland, and this is the Mid-Atlantic Ridge coming down here. And here are a set of magnetic stripes. They've simply been put white when the magnetization is one way and black when it's the other. I think black is the normal direction here, and the white ones are the reverse direction. This is the axis of the ridge. This is the stripe which is being formed today whenever there's a crack, whenever the crack opens and some lava comes out, it's magnetized in this direction and contributes to this stripe. And you'll see the pattern is pretty clearly symmetric on both sides. There's 2 dark ones there, 2 dark ones there, 3 little ones in between, 2 or 3 little ones in between here. It's a bit of a mess. But the pattern is more or less symmetric about the axis of the ridge. And in fact, when you look at the pattern in detail, you find it does reproduce on both sides the pattern which Cox found in the lavas on land. So that now we're in a rather good state. This is the same bit south of Iceland. You can color these up. Well, let's always make this one red, always make that one dark green, and this one blue, and that one blue, and these others orange and green. And you can go all over the world finding these patterns, spotting the similarities, and coloring them up. So then, gradually, as you do this, you find that the whole of the oceans become striped like a colored zebra. Here's a bit of the pattern off the coast of Canada, in the Pacific coast of Canada. This is Vancouver Island. There's a ridge here, and there's another bit of ridge down here. They're separated by this fault here, and you have these same patterns on the 2 sides. Same pattern here, the pattern here. These patterns were first discovered a good many years ago, in about the mid-50s, by Vic Vacquier and his colleagues at Scripps. And this is the Vacquier map. This has not been colored, and it hasn't just been made black and white. The actual strength of the magnetic field has been contoured. But you see these same lines and another lot of lines here cut up by what are pretty clearly faults across them. This is the start of the Canadian pattern up here. San Francisco is here. And these things were found in the mid-50s, and no one had the slightest idea how to explain them. Many people spent a great deal of time thinking about them. I wrote an article, a review article, on the magnetization, magnetic measurements at sea, and I couldn't make head or tail of them. And the reason I couldn't make head or tail of them was that the ideas of the splitting open of the ocean in the middle were only just beginning to come, and I just hadn't connected the ideas. The penny dropped for a man called Fred Vine, who was a student in my department in Cambridge, and another youngish man, Drummond Matthews, who was looking after Vine when he was working for his PhD. And they were working in the Indian Ocean. They were in a survey ship in the Indian Ocean, going backwards and forwards, making these magnetic surveys, and they had plenty of time to think about them. And suddenly one day, they thought what it was. The idea of the splitting in the middle had been suggested by Harry Hess at Princeton. Harry Hess was the most enthusiastic pursuer of marine geology. He's the only man I know who became both an admiral and a professor. He started by being a professor, and before the war he was going out a good deal in American naval submarines, and I thought very unwisely decided to join the Naval Reserve because he thought he'd then have some connection with the Navy. It's in fact a great mistake because, of course, he was the junior person present always, as he'd only just joined it. But anyway, during the war, he got put in charge of a supply ship that went across the Pacific, and he managed to get a very good echo sounder put in it and discovered some wonderful things about the Pacific by always going on different courses across to the Philippines, and eventually got made an admiral. Well, he had the idea about the splitting of the oceans somewhere about 1960, and Vine and Matthews thought of this idea of the meaning of these stripes about 1963, and Cox really made it certain that the things really represented reversals of the field very shortly after that, and also these earthquakes, the nature of the earthquakes along the mid-Atlantic ridge came soon after that. So I haven't described things in the order they were discovered. I've described them more in an order that makes it obvious what the meaning is. But as so often in science, the order of discovery was different, and the puzzles were much more puzzling than they look afterwards. This is a rather larger area. There's been a good deal more survey done since those first ones were drawn. And this is, again, the coast of Canada and the coast of California. It's a somewhat amateur piece of art, but it does show this ridge axis here, a ridge axis here, and a ridge axis down here, and no ridge axis off San Francisco. Off San Francisco, you've only got the yellow and blue and purple bits. You've only got this bit. This bit is all missing. And as I'll probably talk about this at the end, what has happened is that America, in its rush away from Europe, has overrun the ridge that used to be down here somewhere, and only a part of the pattern exists here, more of the pattern and the ridge part still existing up here. The whole thing has got run over. And the reason it was so difficult to understand the pattern when we only had this bit was that there was no ridge. And it wasn't obvious that these stripes had anything to do with the mid-ocean ridge, because there wasn't a mid-ocean ridge anywhere down here. This bit was known. This bit wasn't really recognized as a ridge, I don't think. And certainly there isn't a ridge down here. And that was what made it so difficult to see what was happening. It was when Vine and Matthews went to the Indian Ocean and did a bit of survey over the ridge there that the penny dropped. The survey south of Iceland was done rather before that, but the people who did it didn't understand it and refrained from publishing it rather foolishly, and really looked rather silly afterwards, because they've been sitting on the essential piece of evidence that these stripes are symmetrical about the ridge. And obviously it would have been much better if they'd published it, even if they didn't understand it. Well, now of course we've got a fairly detailed story. We can take one of these lineations, one of these stripes, and we can say that 3 million years ago that was on the ridge. So that we've got, so to speak, a time scale for everything. The whole bottom of the ocean is labeled with dates. Unfortunately, the timetable of reversals determined from the ages of rocks on land only goes back about 3 million years, this part here. The determination of ages on land is not accurate enough to sort out all this part. So that the first thing to do is to say, well, maybe it's been going on at the same rate all the while, and rashly to put dates on all these on the basis of the dates you have on this part. Well, then you have tentative dates for most of the ocean floor. Well, the next thing to do, of course, is to drill and see if that's what you find. And in point of fact, it's worked out awfully well. Just at the right time, the deep-sea drilling project got going. The deep-sea drilling project, called JOIDES, is a joint operation by 5 United States universities. Let's see the Scripps, Woods Hole, Lamont, someone in Florida, University of Florida, and I forget who, the 5th is, I think, University of Oregon, but I'm not sure. Anyway, there are 5 universities who have jointly set out to spend the taxpayers' money drilling holes in the bottom of the ocean. And like all these things, it started as a fairly modest budget, you know, $2 or $3 million a year, and gradually, and it's now somewhere around $15 or $20 million, and it's had to be made an international project, and it's now the International Deep Sea Drilling Project, and there's a promise of $1 million a year from the Russians, and half promises from a number of other people. So it looks as if it'll go on, at any rate, for another 5 years. Well, I've got a few pictures of the operations. This is the drilling ship. It's a ship with a drilling rig, very like a drilling rig on land, mounted on it. The ship cannot be anchored in deep water. You can't anchor a ship effectively in 2 miles of water. It still drifts about too much, and the cables are too much for a business. It's not, I don't say it's impossible, but it's certainly not prudent to try and anchor a ship and keep it still in deep water. So the ship is fitted with engines so that it can move about in any direction and keep itself over a given place in the bottom. This ship not only has the usual propellers at the back, it has propellers on the sides, here, and 2 on the other side. And I think for good measure it has a propeller in front as well. So it can move in any direction it likes, and it can keep itself over a point on the bottom of the ocean. There is a bit of a trick, of course, in knowing when you are stationary over a point in the bottom of the ocean. You put down acoustic responders, things which if you shout at them, they shout back. And so that you put a ring of these around the ship about half a mile away, and there's a thing that makes a noise in the ship, and a ping goes out and comes back from these things on the bottom. And obviously, if you're in the middle of the circle, they'll all come back together, so that you can tell where you are, and you can have a computer which turns the engines on and off as necessary using these results to keep the ship fixed. And that's been a tremendous success. It's the one thing that hasn't given much trouble, that you really can keep a ship over a given point on the bottom without anchoring it and without having any connection with the bottom. You don't have to do it enormously accurately. If you're in a couple of miles of water, a couple of 100 feet to one side or the other doesn't matter much. The drill stem will bend that much. This is a picture of the drilling rig again. I have a shrewd suspicion that that is not the drilling rig in this ship, but in an earlier ship that was used for some trial drilling. It looks to me a little different, but I don't know if that greatly matters. The ship that's being used now is called the Glomar Challenger. Glomar for the company, and Global Marine, and Challenger after the oceanographic ship that went around the world in the 70s of the last century. This is some of the drill stem piled up, ready to be used. That is certainly the ship in which the first trials were done. That's not the Glomar Challenger, it's the Cuss. And this is the drilling rig. They've just pulled out. This is a bit of tube. It's just been pulled out by these clamps. And here's the bit that goes down to the bottom of the sea with the thing for pumping water down to move the chippings out as you drill. There's the stock of drilling stem. Here's some drilling bits with diamonds set around them. They don't have to be high-class diamonds you put in a necklace. They're industrial diamonds. There's one seen close up. At first, they just started drilling from the ship and drilled a hole in the bottom and went on until the drill was worn out. And you could drill a couple of thousand feet, something like that, provided you didn't run into anything too hard. One of the unfortunate surprises was that chert, which is a glassy form of silica, is rather common on the ocean floor, beneath the ocean floor, and wears out bits at a great rate. So what you really want to do is to be able to take the drill out of the hole, put a new bit on, and put it back again. But of course, it's not all that easy if you've got a hole 2 miles below you and a current running and 2 miles of drill stem with a drilling bit on the end. It's not all that easy to get it back in a hole. And what you do is you have a cone here, a thing 20 feet across, something like that. And on the end of the drilling stem, you put a little pinger, and you have receivers round here which send a signal up to the ship so that, or the other way around, it doesn't matter which way around you do it, so that you can tell which way you've got to go to get to the place, and you can also tell how far you are if you measure the time the sound takes, so that you can maneuver your ship so as to get into the cone, and then you push your bit in, let it down, and it goes down the hole. And I think rather unexpectedly it can be made to work. Here's the cone going down. Stands on 4 legs on the bottom. Here's the place where it joins onto the tube, and this is the top of the thing. Well, this is one of the cores they've got up. It's in a plastic tube. You drill, you have a hole in the middle of the drilling bit, and as the drilling bit drills, a cylinder of sediment or hard rock, whatever it is, comes up through the hole and goes into a plastic tube and is recovered from while you're drilling. You don't have to withdraw the whole drilling bit in order to get a piece of core up. You can pull the core up in bits as you go along. Here's the core taken out of its tubes in the lab in La Jolla. This is, I'm sure, basalt from the below the sediments. It's the lava from below the sediments, and there's, I suppose, 30, 40 feet there in those racks. And there's now a tremendous collection of rocks from the seafloor, and one is able to look at all the things one wants to look at to make sure we're on the right lines. You can, if you go, say, a few hundred kilometers away from the ridge, and you drill, you expect to find on the surface quite recent sediments. You go down, the sediments get older and older as you go down, and you get to the bottom of the sediments, and the age there should be the age appropriate to the particular magnetic stripe that occurs at the place you're drilling. And then you go through into the lava, and the lava should be of the same age as the bottom sediments. And it works out pretty well. These are the results from the South Atlantic. This is the distance from the ridge. up to 1,500 kilometers, about 1,000 miles. And this is the age of the bottom of the sediments, of the oldest sediments. You don't know for certain that there aren't some more sediments under the lavas, but this is simply the sediments that were found just above the lavas. And I think, in fact, there won't be any underneath. And as you see, the further you go out, the older it gets. And you now know from the age and the distance how fast it's moving. And this in the South Atlantic, the line is 2 centimeters a year. So it's been moving pretty steadily at 2 centimeters a year back for 70 million years. So, well, this kind of thing, when repeated in various places, is, I think, completely convincing. I mean, after all, these are predictions. One's predicted that this is what would be found, and this is what has been found in the drilling. And I think, for me, the drilling removed the last doubt that the picture was all right. Well, now, what goes with this? We are making new ocean floor at quite a rate. If the two sides move away at 2 centimeters a year, that's a total widening of the South Atlantic of 4 centimeters a year. And in some other parts of the world, the widening is more rapid and as much as 20 centimeters a year. Oh, I should say, I'd forgotten the slide, I should say that this is the little bit of reversals I showed you before, the ones that were discovered in California and could be dated from work on Californian lavas. Those are up here, going back about 3 million years. And then you find the whole story of a much longer time spread out on the sea floor. And these are the reversals back to 76 million years ago, the whole history of the oceans. Well, there are some rocks older than that, but it's a picture of most of the oceans, the pattern of reversals. Well, now, we are making seafloor in a most profligate way, 4 centimeters a year, 10 centimeters a year, 20 centimeters a year, and you can't go on doing this kind of thing because there's nowhere to put it. You're all right in the Atlantic. Here are the earthquakes down the middle of the Atlantic. Here's where new sea floor is being made in the Atlantic. And the Atlantic is widening on the two sides, and presumably the South America is moving away from Africa, and Europe is moving away from America, or America is moving away from Europe. There's not much in the way of earthquakes along these shores or along the shores of Africa or South America. There doesn't appear to be anything funny happening at the continental edges, and one must suppose that the continents are moving with the sea floor. The sea floor is moving out here, the continent is going with it, and the same thing here. These are the peaceful coasts of the world, the Atlantic-type coasts. Same thing around the Indian Ocean. This is quite a quiet coast. India is quite a quiet coast. Australia, Antarctica, very few earthquakes. These are the earthquakes in the middle where the ocean is widening. Well, as I say, if you go on for 100 million years at 20 centimeters a year, you will make, I think it's, let's see, 20 centimeters a year for 100 million years. You make 20,000, isn't it? Well, it's either 2,000 or it's 20,000 kilometers of new sea floor. And if you go on much longer than that, for any appreciable fraction of geological time, all of which is 4,000 million years, you're clearly going to make much more sea floor than there's room for. So it's desirable to get rid of it. Well, now, the obvious place to get rid of it is to look at the other places where there are earthquakes. There are earthquakes along the coast and just inland in South America. The same thing, New Zealand, Tonga, across here, across northern New Guinea, up round the Pacific, past Japan, round the Aleutians. and also this branch down here, and round the Indonesia. Well, now, these earthquakes are really very remarkable. The ones on the seaside are shallow. The ones on the continental side are deep. There's a sloping plane of earthquakes going down under the continent. And the same thing over here, same thing under the Aleutians, same thing under the Dutch East Indies. I'm going to talk about California later. With any luck, I shall run out of time before I have to. Well, here are these earthquakes. You can see them again, the Aleutians, Japan, around here, down Tonga, New Zealand. And these are the deep ones, under Kamchatka, down under Japan, and the outside ones are shallow. Well, the idea is that here's a plate coming along, and here's a continent, say Japan, and here's a plate deciding to go down and disappear. This material came out of the interior of the Earth on the axis of the ridge, and it's traveled out, and it's now going back inside the Earth, where it'll go down and eventually start to melt and get mixed up with the rest of the material down there. But as it starts to melt, the lava that's formed by melting it, some of it will work its way up and form volcanoes. That simply shows the earthquakes under Tonga, how this is the Pacific, and this is downwards, and this is the plate going down with the earthquakes along the top edge of the plate. Well, I think the occurrence of these earthquakes on these inclined planes is rather strong evidence that something is happening going from the surface down into the Earth. And as we have this very strong motivation for getting rid of plates, it seems natural enough to suppose that the new ocean floor that's made here is got rid of along the Andes, under the Andes, and under Tonga. This seems quite a reasonable idea. There are earthquakes going down, and it seems natural to suppose that the new ocean floor that's made goes down the drain in this way. And the same thing for the Indian Ocean. It's made here. Africa moves away without anything happening at its coast. On this side, ocean floor is destroyed around Indonesia. India moves away quietly. Around Indonesia, the material moving from here and from here is destroyed. Well, this introduces the idea that if you want to understand what is happening in the oceans, you look at the pattern of earthquakes. And this is a worldwide pattern of earthquakes. There's a line, this line of earthquakes is the mid-Atlantic set. Here's South America and here's Africa. This is the Indian Ocean, mid-ocean ridge. And this goes round south of Australia and into the Pacific and disappears into California. Well, these are the places where ocean floor is being created. And these sloping plains of earthquakes are the place where it's being destroyed. So that you have two kinds of earthquake belts: the creation ones, where ocean crust is created, where plates are made, and you have the earthquakes like those around the Pacific and around this side of the Indian Ocean, where plates are destroyed. And you begin to see a large-scale pattern in geology. And as Dr. Carmichael was saying, these sorts of things are rather new ideas for the traditional geologist. The traditional geologist had his fingers burnt too often. That's to say, he'd invented worldwide theories which fell down on him in one way or another. And it was, even 10 years ago, and certainly 20 years ago, extremely unfashionable to speculate in a global way. In fact, if you did it, you were clearly a crank. And so this kind of thing is something rather new in geology. It's a worldwide picture of events in which you have these large plates which are colored here. There are 6 large ones, 1, 2, 3, 4, 5, 6. This one is the same again over there, isn't it? I think I don't count that as a large one. If you want 6, you better count that as the 6th. 1, 2, 3, 4, 5, 6. That's it, yes. And then there's some smaller ones. This one, a little one in there, probably several in there. One here, and some lot of little ones in here. So, but you have 6 main plates which are being created and destroyed at places which are marked by earthquakes. Well, now, geology is to some extent, and to a large extent, an account of past events. Well, so far, I've rather been talking about future events. I've been talking about the Atlantic Ocean getting wider and how we can't have this going on and so on without getting rid of some of it. But this is also, of course, a story about the past. That if the Atlantic Ocean is getting wider, it must have been narrower in the past. Well, how narrow is narrow? And in point of fact, this is the Atlantic. Here's the ridge down the middle with its crack. And here are the continental shelves. These are really part of the continent. And the ocean is widening along this crack, and Africa is moving away from South America, so that previously South America was nearer to Africa. And how near will it go? How closely can you fit it? What you want to fit, of course, is the real edge of the continent, the edge of the continental shelf. There's no good trying to fit the coastline. That's rather accidental. This is, as I explained last time, this is the real edge of the continent. How closely can you fit it? And the same thing up here. How closely can you fit it? Well, the fit is really astoundingly good. One wouldn't have believed it. And the extraordinary thing is that this was suggested, well, it was actually suggested by a real, genuine copper-bottomed crank in 1840-something. A Frenchman who was interested in the origin of the Indians. And he believed that North America had been attached to Europe and the Indians had walked across and then gone away. And so this had all happened in the last few thousand years. And he wrote an entertaining book called La Création, c'est mystère dévoilé, which described all this. And the thing was, this was, as far as I know, completely lost, and it didn't have much effect on anyone. There was one Englishman who wrote a book for children about minerals and the earth, and he reproduced the Frenchman's pictures in a book called Mr. Pepper's Playbook of Metals. And, but apart from that, I don't think anyone ever paid any attention. And it was not really until the beginning of this century that the thing was taken up seriously. There were a number of people at about the same time who became interested in it. Certainly the most effective of them was Wegener. And Wegener drew a diagram like this, but unfortunately it was only a rough sketch. It's really a shocking piece of work. It's been faked all over the place. It isn't, the shapes fit quite well, but they aren't much like the actual shapes. And in particular, India is 3 times the proper size. He did the Indian Ocean as well, which I'll show you in a minute. But anyway, it's, I think, somewhat remarkable, and perhaps is characteristic of the non-numerical nature of the old-fashioned geology, that no one was sufficiently interested to try and fit the things decently. It's not all that easy to do, because, of course, you can't represent the Earth correctly on a flat map. And if you take a map and cut out South America and try and fit it into Africa, well, the fact that the thing's projected onto a flat plane will upset things, and you have to do the fit on a sphere and then map it onto the flat afterwards. But if you cut out things on a sphere, you can do it. This was actually done by taking latitudes and longitudes along the continental edges and letting an industrious computer fit them together as well as they'd go. And the fit is really astoundingly good for Africa. This red thing is an overlap, and it's the Niger Delta. The Niger Delta has obviously been formed since South America separated from Africa, and naturally, if you put them back, it's an overlap. There's a certain amount of faking has gone on up here. Rockall Bank has been left in, and Iceland has been abolished. I think the abolition of Iceland is very natural, because Iceland is in fact a piece of the mid-ocean ridge. It is entirely formed of volcanoes which have been produced since the split, since the Atlantic opened. A good deal of work's been done on this because a fit of this sort stimulates all kinds of work. I mean, it becomes very important to see whether Iceland has been justifiably abolished. I mean, if Iceland had a piece of continent in it, it would be unfortunate. On the other hand, this thing, which is the Rockall Bank, is underwater today, except for a little pinnacle about there. And in making this diagram, I chanced my arm a bit and said that we need that badly. We need the Rockall Bank as a piece of continent. And I'm going to put it in, and we better have a look to see. So then we had a look to see, and it turned out to be continental, I think, beyond doubt. Well, this is rather characteristic of the procedures of science. The best way to proceed is to trail your coat and say that you're being very arbitrary and you're going to assume what no one knows, that the Rockall Bank is a piece of continent and this weakens your case and so on and so forth. And if you're pretty sure it really is a bit of continent, as I was at the time this was drawn, one can quite safely say how foolish one is being. And then when it's subsequently demonstrated that it is in fact a piece of continent, of course this enormously strengthens your argument. You've made a prediction. But if you say beforehand that you know it's a piece of continent for this, that, and the other reason, then it's not nearly so good. You want to demonstrate it's a piece of continent afterwards. The other fake is the rotation of Spain. The Bay of Biscay has been closed, and Spain has been rotated. And it's also been moved a little bit in this direction. Well, if we didn't do that, it would overlap Africa, which seemed unfortunate. And again, there was some reason for supposing that Spain had rotated. There's the compression along the Pyrenees, and that led to some difficulties, actually. And there was some evidence from these fossil compasses that are distributed about the place that the thing had rotated. They didn't point either north or south, they pointed cockeyed. I mean, if a rock was formed when the thing was like this, the thing would point like that, and when Spain rotated into its present direction, the compass would point like that. So the fossil compasses in Spain point about northwest instead of north. And this is associated with the subsequent rotation of Spain. So that again, this turned out to be so. And also, you can regard this as more than a jigsaw puzzle. You can, it's got a picture like a jigsaw puzzle, that all these edges have a geology, and not only the shapes, but also the geology ought to fit. This area here has 2,000 million year old rocks on land, and this has 500 million year old rocks. And the border runs about like that. And if you take that across into South America, which is a very narrow continental shelf, there's not much doubt about the extrapolation, you come to a little village called San Luis. And the rocks on one end of the village are 2,000 million years old, and the ones on the other end are 500 million years old, which is extremely satisfactory. Well, I'm going to skim rather rapidly through the Indian Ocean. I don't want to talk about the Indian Ocean. Here's Australia and Antarctica as they are now, with the earthquakes and the ridge in between. And here they are fitted together. They fit really very well indeed. And moreover, there's some shallow stuff out here, which has been split down the middle and fits very well indeed, a thing called Broken Ridge for obvious reasons. I only want to remark here that India has moved northwards. It's moving in this direction at present and has collided with Asia. And the Himalayan mountains are, I think, pretty certainly associated with a collision of India with the south of Asia. Now, here's a picture going backwards in time. This is 36 million years ago, India a good deal further south, Australia and Antarctica nearer together. This is 45 million years ago, Antarctica and Australia together. I'm not quite sure what they've done with India. Oh, it's the picture's turned around. It's up here. Here they are coming closer together still, and we've already talked about the fit on this side. Well, the man who drew these diagrams, Dan Mackenzie, in my department in Cambridge, is a bit of a purist, and he said he couldn't make up his mind how they fitted together closer than this, so he didn't draw another diagram. But it's pretty obvious that, that most of these things are going to close up, and we know that this can close up. And here, oh, this is a picture of the collision. Here's India coming along, an old plate going down under India, and an ocean now disappeared between India and the south of Asia. Volcanoes being formed up here, presumably. Here's the collision, India slithering under Asia, and a mountain range being formed. And the trenches now, the trench here and the downgoing plate are now going to go. The continent is too light and it can't sink, so it stays up. That's why continents are old. They're too light to sink. And this thing seems usually to break off and to go down on its own. And under the Hindu Kush, there are in fact some earthquakes down here, which probably represent the extinct plate going down. In the future, there may well be another trench and another plate start here, but it hasn't started yet. I think I'm going to omit this altogether. I haven't really time. What the blazes happened to this? There should be 2 or 3 slides. That's the most extraordinary thing. I know I put them in. Just see if you can find some more slides. Doesn't matter if you can't. They were a little separate packet. Well, never mind. Let's talk without them. I promised that at the end I would say something about California. And the reason I hesitated and left it to the last minute was that the events have been a little complicated. As I said, North America has been moving away from Europe and has been approaching a ridge of which we can still see parts. It exists off South America, it exists off Central America, it exists off Western Canada, but it doesn't exist off California. And what has pretty clearly happened is that there was once a ridge there was once a downgoing plate going down under California, and there were volcanoes arranged inside rather than the way the Andes are arranged along South America, and the whole thing has been run over. California, in its impetuous movement westward, has run over the trench and the ridge, and the whole thing's gone, and it's run over the magnetic pattern, and there's only part of the magnetic pattern left. Well, today, the ridge runs into the Gulf of California, where there are a lot of little bits of ridge spaced like that, which are still spreading, and these bits of ridge are more or less across the Gulf, and they're still spreading and producing new seafloor. They're really very convincing. I never quite believed this story till I went there and sat up at nights watching the echo sounder. And the whole of the coastal part of California, the whole of the part on the seaward side of the San Andreas Fault is, as every Californian knows, moving northwestward along the fault. And so that you have, the reason it's complicated is there are two stories. There's the older story in which California moves westward and runs over the ridge, which still exists to the north and the south. And there's the story of the spreading in the Gulf of California and the motion of the coastal regions on a fault, which essentially joins the bits of ridge in the Gulf of California to the bits of ridge off Canada. So that it is sort of one more complicated than the things I've been talking about, and there are certain difficulties. The thing seems to be moving more rapidly in the northern half than the southern half, and there's this bend roughly level with Santa Barbara, where the San Andreas Fault takes a bend, and there must be, in fact, there's known to be compression there. It's sliding past in Southern California, it's sliding past in Northern California, and by Santa Barbara, where there's this bend, there is compression going on. If it had been at sea, it would presumably have developed a downgoing plate, but as it's on land, it has difficulty in sinking, and it's simply rucking up and compressing the mountains between Santa Barbara and Los Angeles, and you get these large earthquakes in that region of a compressional kind. Well, let me, at the end, say what a pleasure it's been to come here, and how much I'm enjoying myself, and how much I appreciate having an audience this time, which I think is even larger than the audience I had last time. I always have sort of feelings there'll be 20 people. I did once give a lecture in the University of Sussex, where various things had happened, such as the lecture being advertised for 2 different places and 2 different times, and some frightfully with it pop left-wing anarchist was also speaking at the same time, and 5 people turned up. So we went off to a pub. And I thought that might happen here. Yeah, sure. Well, yeah, you talk on that one. So I've been told to keep this one on.
I think Professor Bullard will prepare to answer some questions, but as you can see, his lecture gained some impact by the anecdotes and the little side observations he makes. And I think it's probably not inappropriate for me to make some side observations about how he's behaved since he's been in Berkeley, California. Well, under the terms of the award of the Hitchcock Professorship, as I'm told them by Mrs. Sponseller, who very kindly and generously arranged the visit of Professor Bullard, under the terms of this professorship, he apparently is allowed to travel first class on an airplane. And this is practically a unique occasion in the University of California. So I went down to the airport to meet Professor Robert Bullard, and as he walked off the plane, I'd never met him before, I expected to see his wife. And his wife was not there, and I sort of tried to explain, having never met him before, where his wife could be, and out it all came. My dear chap, she's coming on the Greyhound bus tomorrow.
But she was coming from New Zealand.
You've got to allow me to tell my stories. And as you know, those of you who were here last time, you were very intrigued with what's happening in California. I think it was on Wednesday this week, after lunch, where the faculty of the Department of Geology and Geophysics have lunch, I listened to a conversation in the corridor between 2 of our seismologists and Professor Bullard, looking at a map of California, which happens to be upside down, saying, "For heaven's sake, tell me what's happening in California, because I'm sure someone's going to ask." And if any of you like to ask questions, do so. Professor Bullard will
Yes.
answer.
Where is the African plate
Well, the African plate is being formed in the South Atlantic, and it contains the eastern side of the South Atlantic and the Africa and the western side of the Indian Ocean. And there you've got another lot of floor creations. So the African plate isn't being consumed. The two ridges in the South Atlantic and in the Indian Ocean are moving apart, and the plate is being consumed in Indonesia. I mean, you see what I mean? You've got two ridges with a plate in between, and this plate in between is getting wider and wider, not being consumed, and the consumption is in the far eastern side of the Indian Ocean. You look A, mystified, and B, dissatisfied. This is an odd thing, and I think, is it a unique case? I think it is. It's a bit surprising that you've got two ridges with no trench in between, which means inevitably that the two ridges are moving apart. Let's go along the row. You, yes?
It seems a rather long ways from the East Pacific rise to Japan. Has the seafloor all the way across there come out of the East Pacific rise, or is there an edge?
Well, look, I think the answer to that one is I don't know, and I don't think anyone does. There's, you see, there's this very curious feature which I think no one understands of the Hawaiian Islands and the Emperor Seamounts. And exactly how they got there, the official view at the moment is that there's a hot spot in the mantle and the plate is passing over it and producing all these volcanoes. And if this is right, then it must all be moving as one plate. It may well be the lineations, or magnetic lineations off Japan, are older than anything in the Atlantic. Well, yes, I think they are. There are some old ones in the Atlantic too, but they're Jurassic and getting on for 200 million years old. I don't know what, 180, something of that sort. And these older lineations have not been examined with the detail that's necessary. We want a good deal of drilling to get the ages that correspond to them and so on. And as far the obvious thing is that it has all come from this ridge. Whether this proves to be so or not, I think time will show. Yes, wait, let's get, yes.
One of your pictures showed Australia apparently heading for a subduction zone. When will this happen, and what will happen when it reaches?
Well, the subduction zone north of Australia, it's actually north of New Guinea, is going down the other way. Australia is moving. There are two things may happen. Either the subduction zone may go along with Australia, go in front of Australia, still consuming Pacific floor, or of course it might be that Australia overruns the subduction zone, rather as California has overrun the subduction zone. I'm not a prophet, and I don't know which will happen. Yes?
How do you account for the lack of vertical movement along the San Andreas Fault?
Well, how do I account for the lack of vertical movement? There's a certain amount of vertical movement in the Santa Barbara area, isn't there? But why would you expect vertical movement particularly?
Well, overriding, you have the vertical movement along the trench in South America, do you not? We do not have it.
Well, because your plate, you've not got a plate going down. You've got the two things moving sideways, moving along each other. Yeah, but the pressure is along the fault. I mean, the fault's moving like that.
The captain of engineers by the name of Cox had charge of surveys following out 6 on the peninsula.
Mm-hmm.
And he sent his crews back for about 3 weeks. They made a mistake of 3 feet. They found it all in the compression in the shatter zone. And you can see it in earthquake country in the bending of the perfectly good board fence that can't be stretched, in which the posts in the fence follow the curve of about 60 foot, and that zone was compressed 3 feet according to him.
Yeah. Well, and what you're worried about, this ought to be associated with vertical movement.
Well, that straight down, doesn't it? Or it couldn't.
Yeah.
So there's no override.
Well, I don't know. It does seem odd, doesn't it? Look, as I say, I've only very recently discovered anything about California. Would anyone like? There are plenty of Californian geologists here. There are lots of Californian geologists. Ian, what?
It's all yours. You're the
All right. Yes?
What did you do with the transits when you put in that map?
Ah. Well, of course, there is one thing, and that's fairly certain, I think, that apart from the little patches I've mentioned, most of the Atlantic Ocean has never been continent. I mean, except in the sense that when it was shut up, that there isn't a lost continent in the middle of the Atlantic, apart from this Rockall rise off Scotland. And one or two other little bits. I remember once we found a nice little bit off Portugal. There's a beautiful shallow piece of sea separated by deep sea from the mainland of Portugal and with faults all around it. And I thought how awful it will be if when we take photographs on this, we find Phoenician temples or something. and it really is the lost Atlantis. We shall spend the rest of our lives photographing this place and working on it, and I don't want to do that. But fortunately, we took the photographs, and there was nothing but miles and miles of sea pens, which is a little animal about looking like that. And the whole bottom was covered with them, and there were just bare limestone underneath them. Yes?
Have you ever had a chance to really drill through the surface, through the mantle, and get below there?
Well, you needn't even drill through. Well, you know what? Of course, you know what happened when the suggestion for drilling through the mantle. Congress cut off the funds, and I thought Congress were quite right. They cut them off for the wrong reasons, but, connected with Democratic Party politics. But anyway, there was a proposal for drilling through the whole crust of the Earth into the mantle. And this came to an end, and instead we got the drilling project I've described, which has been much more useful. And I think we now know enough about it so that we can look for places where the mantle actually sticks out. For example, in Cyprus, there's a very clear example. And my Californian friends tell me that about 30 miles north of here, you've got some nice sea floor pushed up on land, with basalts underneath it and serpentines under that, and maybe this is the upper mantle, the bottom of this. But I think it's quite clear that St. Paul's Rocks, for example, in the South Atlantic, and Cyprus are fair samples of the mantle. Cyprus is particularly convincing. Yes. You know, we're not going to get through all these questions, are we?
Conclude that the Pacific will shrink and the Atlantic grow until they're roughly equal. How can you account for all the land on one side of the globe originally?
Well, you see, I think this is what Wegener said, but I think Asia was probably split up. You see, there clearly must have been an ocean of some sort where the Urals are now. If the Urals are practically the only mountain range in the world that runs through the middle of a continent, and I think it's very probable that there was a split there, and that a large part of Asia was way over to the east, and maybe split into several bits. But of course, Russia and China are not in the highest degree accessible for these kinds of investigations. But I don't think that block was as big as some people say. I think it's embarrassingly big, but I think you can remove most of Asia from it, probably. Look, we ought to give the people over the other side. All right, quick one. Well, I don't know how far it's analogous. It's a nice big mountain. It isn't as big as the Himalayas.
Two continents have collided.
I would have thought so, yes.
Well, my question is...
But look here, I don't know, you see. There may... I mean, the mountains may have been formed before they collided. I don't know. I don't know anything about the Urals. The only thing I know about the Urals is I've seen them in the Dr. Zhivago film, which, of course, was taken in Spain. It was taken in Spain, of course.
So why in the 4 or 5 billion year history of the Earth haven't all the continents collided and stuck together?
Well, they break again, you see, they split again. Like South America splitting away from Africa. I mean, I think the process of splitting and collision has gone on all through geological time, probably, although it's fairly speculative. Yes.
When was the most recent magnetic reversal?
Seven,
Are there any phenomena associated with it?
the most recent one that's certain was 700,000 years ago. Look here, there are phenomena associated with it. Come and ask me about them afterwards, because it isn't really very relevant. There's a possible one about 20,000 years ago. There's some reverse lavas in France. They've mostly now, most of the lava flow concerned has been removed by people interested in paleomagnetism. I think we ought to stop.
Professor Bullard, I think, is going to run out of his voice. On your behalf, I'd like to thank Professor Bullard and welcome him and his wife to the University of California at Berkeley, and thank both of them for coming and giving us a most enjoyable lecture.